Hello there, my name is Ogodino Uche Jude. Welcome to today's physics class. So our topic for today is nature and production of sound wave. The class is SS2, week 7. So at the end of the lesson, the student should be able to describe the production of sound by vibrating sources, describe the longitudinal nature of sound waves in terms of the processes of compression and rarefaction, and deduce that a medium is required in order to transmit sound wave. The speed of sound differs in air, liquid, and solid. So the nature and production of sound. Sound is a form of energy that is transferred from one point to another as a wave. Sound wave and longitudinal wave. Okay, we discussed wave in our previous class, that's last term. We said that a wave is a form of energy that is traveling from one point to another, carrying energy and requires medium. And this particular energy does not displace the particular medium itself. So for any wave to occur, there must be a source of what? Vibration. For sound wave to occur, there must be a source of what? Vibration. And sound wave falls under longitudinal wave because this sound will travel in the same direction as the mode of propagation. The way it is being produced, it follows that direction, just like in a slinky. Okay, now, having said that, sound is produced by vibrating sources placed in a medium. We've said that before. For sound wave to occur, there must be a vibrating source. There must be something disturbing the air molecules to propagate that sound or carry that sound or let the sound travel to a particular hearing. So the medium is usually air. Yeah, that's common. The air is a common source of what? Propagation, or the medium by which sound wave travel. But it can be gas, liquid, or solid. A vibrating object in a medium such as air produces sound waves by shifting the layers of air. Okay, we are going to understand this better with the next one. So examples of vibrating sources are the loudspeaker and the tuning fork. So for sound wave in air, compression and rarefaction can be thought as changes in air pressure. So before we come to this, let's go to this particular one. This is our tuning fork. Our tuning fork now, anywhere is being placed, there is surrounding air molecules around it. Air molecules moving around it. Now these air molecules in this particular diagram, you see a straight line, evenly spaced, the same spacing, means that the air molecules are not disturbed. But immediately the prongs of the tuning fork is being hammered. If you hit it with a hammer, the thing begins to what? Vibrate. And when it's vibrating, then it starts disturbing the what? Air molecules. So as it's vibrating, the first part of, or the molecules of air closest to it at this particular point now becomes more compressed. The molecules becomes compressed. Now, furthermore, if you look at this region where you see your R, the molecules are not as compressed as the other, and the circle continues compression where there is higher air pressure than normal. This one is called our rarefaction, is where there is what? Lower air pressure compared to the initial case when the air molecules was not disturbed. So we have two regions. We have the compression region and we have the rarefaction region. This is another diagram depicting that if this was hammered and it started with rarefaction, the next will come with what? Compression, and so on and so forth. So going back to this, for sound waves in air, compression and rarefaction can be thought of as changes in air pressure. Compression are regions where the air pressure is slightly higher than the surrounding air pressure. And rarefaction are regions where the air pressure is slightly lower than the surrounding air pressure. So another demonstration is our loudspeaker, which is a source of what? Vibration of sound. Now this loudspeaker, look at this first region. This first region here is the undisturbed molecules, but immediately the speaker is getting sound signal from the radio itself or whatsoever, or the audio player. Then what happens? There will be two regions of what? Molecule air pressure. There are two regions of air pressure. This region, this particular region, where you see the air like clustered together, packed together, is called a region of what? Compression. And this one, where the molecules are evenly spaced, they're not compressed together like that, are called a what? Rarefaction. And so they travel to whatever source they want to what? To end at, especially our listening ears. So That is how the sound wave will move. It will move through the medium air. So if we liken this now to the what is this called now? The wave graph, our wave graph now. This region, this particular upper region is called our what? Air compression or compression itself. This particular region is called the compression, and you can see this is what at maximum amplitude. And this other part where it is evenly spaced is likened to our what? Rarefaction, and so on and so forth. So transmission of sound. Sound waves are mechanical in nature in that they require a medium to propagate, yes. Unlike light waves, which are electromagnetic in nature, sound waves cannot pass through vacuum. So this place is actually telling us that we need a medium. Mechanical means that we need a medium for what? Propagation. We need a medium to carry the source of vibration. If I'm scratching my leg or trying to make some screeching noise on the floor, that noise is going to be carried by what? A particular medium, and that medium is mostly what? Air. So the air carries the sound wave to our hearing. Now, if you compare it to light waves are electromagnetic in nature, and electromagnetic wave does not require material medium. They are not mechanical in nature, and so they are radiated, or they travel to what? Ordinary space, which is called vacuum. So the Berger experiment is to support the fact that sound waves require a medium such as air for propagation. A very good example now is this bed jar. This is setup of a bed jar. So the diagram, this first one is to your power supply, connecting wires. Then this is like your ringing bell at home. So we call this one the bell jar. So this is the bell. Now, what actually happens here is after this setup, if everything is connected correctly, then you plug to a source of power. What happens? This thing begins to ring. Now there is a vacuum pump. There's a space for vacuum pump. This vacuum pump is connected, but initially this vacuum pump is not what? Connected, so that when this bell jar is connected to your source of power, you begin to hear, or you see this the striker, this hammer. You see this hammer hitting this gong, and you hear a lot of noise, the sound wave being carried by the air. But immediately you on or you put on this vacuum pump, the function of the vacuum pump is to suck air out of this bell jar. So when the air is being sucked out of this bell jar, what happens? Immediately it starts sucking it, the noise begins to reduce. From the loud noise or the loud sound we were hearing before, you begin to hear a lower sound till finally, if all the air is being sucked out, there will be no, you just see the thing striking the gong. That's the hammer striking the gong, and there will be no sound, showing that we need air for what? Propagation of sound wave. So that is the meaning of this experiment. So we've talked about that. So precaution, this experiment, ensure that the bell does not touch the bell jar. The bell should not touch the bell jar. That is number one. If you are going to perform this experiment in your laboratory, in school, and connecting wires are thin. So the reason is to prevent sound waves from being transmitted through the bell jar, and connect, if you connect if the bell itself is touching the bell jar, then the sound, even though you've sucked all the air, then the sound. Okay, like we were saying before, the precaution for this experiment, in this experiment, ensure that the bell does not touch the bell jar. So if the bell touches the bell jar, then we can't really understand what is actually going on in the experiment, because the bell itself will be hitting the bell jar and there will be production of noise. So you must make sure that the bell does not touch the bell jar. And also the connecting wires are thin, so that air should not pass through a fat or a thicker wire. So you use a thin wire. Those are the precautions. Use a very thin wire and make sure that the bell itself does not touch the bell jar. So the medium of transmission, any medium which has particles that can vibrate will transmit sound, but the nature of the medium which affects the speed of sound, but the nature of the medium will affect the speed of sound wave. In general, the speed of sound in a liquid is 5 times that in gas. The speed of sound in a solid is about 15 times in gas. So this table demonstrates that the medium air approximate speed is 300 meter per second. 300 meter per second, not meter per second square. Sorry for this. 300 meter per second. Then water is 1,500 meter. Then air is 5,000. So it travels fastest in solid. Next is what? Liquid. Then air is the least that sound wave travels in terms of their speed. So effects of physical condition on the speed of sound in air. Physical condition change. The physical condition, when it changes, when temperature changes, the speed of sound is proportional to the what? Square root of its temperature. Then for humidity, sound travel faster when humidity rises. That means if there is what? The amount of water vapor in the atmosphere is higher, then sound wave can actually travel faster. Then pressure, a change in pressure does not affect the speed of sound. So when there's much pressure in what? In the sound wave, this actually does not affect the what? The speed of sound in air. So the speed of sound in air is actually attributed to, or is actually affected by this three temperature, positively or negatively. For temperature, the speed of sound is proportional to square root of its temperature. Then humidity is what? Or the humidity affects it by what? By increasing. That's sound waves travel faster when the humidity is what? High. And if we talk of pressure, when the pressure is lower than or higher, it does not actually affect the speed of sound in air. I take it one more time. For temperature, the speed of sound is proportional to square root of its what? Temperature. For humidity actually has to do with the amount of water vapor in the atmosphere. So sound travel faster when humidity is what? Higher. Then for pressure, the pressure in the air does not actually affect the speed of sound traveling or the speed of sound in air. So pressure from external source or internal sources in the air does not actually affect that. So with this is the end of the slide. So end of the slide. So with this, I hope you understand this particular physics lecture, and I hope that you'll be able to comprehend everything I've said. So make sure you apply them to when you are reading your books, and till we meet again in our next physics class, I still remain Mr. Jude Ogodino.